Welcome to week number 5 for ECE 401, Senior Design 1. In this lecture, we're going to look at diodes and transistors, kind of a review of electronics, if you've had electronics already, or a preview of electronics. So, again, as a reminder, this is one of the courses taught in the Electrical Computer Engineering Department at NDSU. One way to get to this course is go to Bison Academy, the semi-official website for the Electrical Computer Engineering Department. Go under Senior Design 1, and what we've done so far is we've looked at the project management OneNote, kind of a review or preview of using microprocessors in your design, a review of circuits using op amps, voltage nodes, current loops, different type of op amp circuits. Today looking at diodes and transistors. Now the goal in Senior Design 1 is to come up with a circuit kind of like this. This is a custom PCB that will do something. In this case, this one builds a stoplight. So the light goes green, yellow, red, controlled by software. Now, oftentimes the microprocessors are WIMPs. They're only capable of 12 milliamps on the case of the Raspberry Pi Pico. To get more current out, I need some circuits. That's electronics. Basically, electronics are the interface to the microprocessors. On the sensor side, convert the signal to 0 to 3.3 volts. On the output side, take 0 to 3.3 volts at 12 milliamps, crank up the voltage, crank up the power. That's what electronics are all about. So here we're at week number 5, diodes and transistors. So if you're taking Senior Design 1 and you haven't had electronics yet, don't panic. We'll cover pretty much what you need in this class. When you do take electronics, you'll get this in more detail. So starting out, in Senior Design 1, you can choose from a dozen different circuits to build. Again, a good example would be like this little stoplight. Regardless of which one you select, your overall design must operate on 5 volts DC, must have an LED operating at 20 milliamps, plus minus 5 milliamps, must have 1 NPN and 1 PNP transistors, or more, capable of driving that LED, and you must have at least one IC. That could be your Pi Pico, an op amp, a 555 timer, your choice. This lecture covers analysis and design of LED circuits and analysis and design of NPN and PNP electronic switches. So starting out with diodes. An LED is a type of diode. Let's back up a sec. Let's talk about diodes in general. Diodes are a topic covered in 320 Electronics 1, and diodes act as valves. What they do is they allow current to flow one way, but not another. And kind of one way that works, a couple ways to describe this. Here's one way. With semiconductors like silicon, I can dope them. What doping does is I can create two types of charge carriers. In the P region, almost all the charge carriers are plus charges, holes. In the N region, almost all the charge carriers are minus charges, electrons. Now, if current flows P to N, anode to cathode, what happens is I have plus charges flowing in the P region, minus charges flowing in the N region. Again, this is backwards because minus charges are negative, so double negative gives you current in the plus direction. When the two combine, the hole is actually a missing electron in the covalent bond. The electron fills the hole, and the electron's gone, the hole's gone. In this case, I'm using majority of carriers, so going P to N, the resistance is very low, like 0.01 ohm. If I have current flowing backwards, I have plus charges in the N region, and there just aren't very many of them. I've got minus charges in the P region, again, there just aren't very many of them. So when current flows this way, the resistance is really high, like 10 to the 12th ohms. So a diode is like a variable resistor, low resistance in one direction, high resistance going backwards. They basically allow current to only flow one way. Because of that, the symbol for a diode is an arrow. This reminds you that current can flow anode to cathode. It cannot flow cathode to anode. In terms of the VI characteristics, can you cover this in electronics? The VI characteristics for a diode are nonlinear. They're exponential in nature. That makes diode circuits really hard to analyze. It's hard enough analyzing a circuit with n equations, n unknowns. It's even harder to analyze circuits where those n equations are nonlinear. Because of that, diode circuits are just a pain to analyze. So what we do is come up with a model. In engineering, what we typically do is, if I have a hard problem to solve, change the problem. But change it in a way that I keep the flavor of the old problem, but make it easier to solve. So in the case of a diode, I've got diode looking like this. The BI characteristics are the blue lines. That's hard to analyze. That's nonlinear, exponential in nature. Replace that with a linear circuit. So if the diode is turned on, I treat it just as a voltage source. So in that case, it's just a voltage drop. In this case, 1.9 volts. Voltage drop is VF. If current's going backwards, I use this model. That's just an open circuit. So that's your nonlinear model, or a piecewise linear model for diode. It's either on or off. When it's on, the model is really simple, just a voltage drop. When it's off, the model is really simple, just an open circuit. The challenge then is which one's correct. So that's the ideal diode model. I just have black and white, on or off. If it's on, the voltage drop is constant. If it's off, the current is zero. Now the on voltage depends upon the type of diode. A germanium diode is about 0.3 volts, silicon 0.7, red LED is 1.9, yellow is 2, green somewhere between 2 and 3 volts. That's not exactly true. Again, you go back to the actual diode model, the blue line. It's not exactly 1.9 volts when turned on for red LED. It's close though. So if I just want to get close, I can use this model. If I want to get closer, use Circuit Lab. Circuit Lab actually uses the nonlinear model. If you take a diode in Circuit Lab, like here's a diode, double click on it, there's a bunch of different diode models for it. These are the nonlinear models for it. This defines the exponential relationship. So you can modify these if you want, or just click on different diodes. The main one that we use is the 4004. That's a generic silicon diode. If you design a circuit in Circuit Lab using diodes, I can then analyze it. Now to analyze it, there's DC and AC. If I do DC analysis, this would be like your microprocessor trying to turn on the LED. If this is 5 volts to turn it on, I can analyze it. Now analyzing this by hand is really hard because this is a nonlinear circuit. That's a nonlinear element. The beauty of the ideal diode model is it makes the circuit analysis a lot easier. A little bit wrong, but a lot easier. So in this case, about 5 volts, I'm trying to push current through the diode, anode to cathode, so it probably turns on. This is a silicon diode, so when it turns on, I've got a 0.7 volt drop across it. So that tells me right away that V2 is 4.3 volts. If this is 4.3 volts, I know the current is 4.3 milliamps. That was pretty easy. That's why we use the ideal diode model. Makes analysis a lot easier. If I throw this in Circuit Lab, I can see that my answer is wrong, but it's close. V2 is not 4.3 volts, it's actually 4.335 volts. The current is not actually 4.3 milliamps, it's 4.335 milliamps. Close, but a couple percent off. That's typically what you see in electronics. I can get close with analysis. If I want to get more accurate, throw it in Circuit Lab, or better yet, build it. But that'll be next week, building it on a breadboard. If I flip the voltage, try to have current going backwards, the diode opens up. So what I would expect with the ideal diode model is this turns off, the current is 0, and the voltage is 0. If I throw it in Circuit Lab, I'll see that actually the voltage is not 0, it's negative 76 nanovolts. The current isn't 0, it's actually negative 76 picoamps. So again, it does conduct a little bit of current, but a picoamp is really, really small. A nanovolt is also small. We have a hard time measuring that in lab. Effectively it's 0. So that'd be DC analysis. If I do AC analysis in Circuit Lab, make this a sine wave, what I'll see is V3, or V1 is going plus minus. When it goes above 0.7, D1 turns on, and V2 is V1 minus 0.7. When it goes negative, the diode turns off, and V2 equals 0. So I have kind of two cases. If I have at least 0.7 volts, this turns on. Less than 0.7, it turns off. I can see that in Circuit Lab. Let's do a time domain simulation. This is 1 kilohertz, so let's run it for 2 cycles, 2 milliseconds. Make the step size 1,000 times smaller, 2 microseconds. And let's look at V1 and V2. When I run that in Circuit Lab, here's what I get. I see that V1 is right here. That's my sine wave. The orange line is V2. When the diode turns on, right here, V1 is more than 0.7. V2 is V1 minus 0.7-ish. When V1 drops below 0.7, the diode turns off. When it turns off, V2 equals 0. Okay, not exactly 0. It's going to be like 76 picoamps or nanovolts. Basically 0. So let's kind of a diode. If you have multiple diodes in a circuit, this is when it gets annoying. I have 3 diodes. Each one is either on or off. So there are 8 possible permutations. One of those 8 is correct. If you have this circuit, I look at it and say the 5 volts is trying to turn on diode 1, trying to turn on diode 2, trying to turn on diode 3. Let's assume they're all on. If they're all on, then the voltage drop across the diode is a constant. This is 0.7 volts. A red LED, that's 1.9 volts. Green LED, depends upon which one you have. One we're assuming is 2.0 volts. I can now find the current. This is 5 volts. The current through the silicon diode is 5 minus 0.7 over 1K, 4.3 milliamps. Through the red LED, 5 minus 1.9 over 2K, 1.5 milliamps. And the green LED, 5 minus 2 over 3K, 1 milliamp. In terms of design, if I know the current that I want, I can find R. By adjusting R, I can change the current. Again, this is a silicon diode. If it's turned on, this is 0.7. This point right here is 1.9. And this point is 2.0 volts, assuming an ideal diode model. I can then find R. For what 20 milliamps, I know this is 5 volts. 5 minus 0.7 over 20 milliamps, this should be 215 ohms. If I want I2 to be 20 milliamps, I've got 5 minus 1.9 over 20 milliamps. That should be 155 ohms. And the green LED, I should make that 150 ohms. So that's kind of analysis of diodes. An LED, a light emitting diode, is just a diode. So the previous analysis that we had works on LEDs just as well. The difference between LEDs is the on voltage varies. The material determines the on voltage. The material tells you the color of the LED. In addition, I've got another term called the millicandles. Now, LEDs are current source or current devices. The current is proportional to light. So on the data sheets, they specify the current that is tested at 20 milliamps and the brightness at 20 milliamps. If I have the current, I'll have the brightness. Wavelength is a more scientific term of color. Again, red is not really a scientific word. This is the wavelength. And cost is what accounting cares about. With LEDs, brightness is proportional to current. So for example, here is a soldering kit you can buy from Amazon. It's got 8 LEDs with resistors. What the circuit looks like, I've got a 9-volt battery, provides power. There's a resistor that I can switch in and out. These are the switches and the resistors, 330 ohms, 470 ohms, 1K, 2K. I've got a yellow LED going to ground. I can find the current through the LED by saying it's this yellow LED about 2 volts. The current is 9 volts minus 2 volts over R. If I look at the 330 ohm resistor, the current is 9 minus 2 over 330, 21 milliamps flowing through that resistor. Also flowing through the diode. The brightness then is proportional. If it's rated at 20 milliamps, 450 millicandles at 20 milliamps, if I apply 21 milliamps, will be that ratio times 450, 477 millicandles. Double the resistor, I get half the current, half the brightness. You can see, as R goes up, the LED gets dimmer. So with LEDs, I can basically control the brightness by controlling the current. Another use of diodes are for reverse current protection. In design 1, you are required to use a 9-volt battery, but the rest of the circuit runs at 5 volts. To do that, we use a 7805 or LM7805 voltage regulator. Now what this does, this dumps voltage. If I feed it anything between 6 and 36 volts, it'll dump the excess voltage and produce 5 volts out constant. So that's how the circuit works. The problem with it is the efficiency. When it dumps voltage, say if I have 1 amp coming out, I've got 5 volts at 1 amp, 5 watts going out. If this is 9 volts at 1 amp, 9 watts in, 5 watts out, this is dumping 4 watts. So it's going to get hot. That's why this has a big heat sink on it. If you're dumping a lot of voltage at a lot of current, it's going to get hot. You need to dissipate the heat. That's the heat sink. So again, these aren't real efficient. You can buy more efficient ones, but they're more expensive. In Circuit Lab, I can check this. Now the rest of the circuit, I don't really know what's going on over there, but I can simulate with a resistor. Or in this case, if I want to drive a LED at 10 milliamps, I'll have 5 volts at this point, 1.9 volts for red LED. To get the current to be 10 milliamps, I want to pick the resistor R2 to be 5 minus 1.9 over 10 milliamps, 310 ohms. So I should have 10 milliamps here. To drive that with a 9-volt battery, I'll have the 9 volts come into the input for the 7805. That drops the voltage down to 5 volts. That drives the circuit. Do a DC analysis in Circuit Lab, I can see I've got 9 volts in, 4.999 volts out, basically 5 volts. And the current is 10.06 milliamps, just like I expected. And note that when you get to Circuit Lab, or even in hardware, the answers won't be exact. This is not exactly 1.9 volts. Circuit Lab says 1.882 volts. When I build it, it'll be something else. It should be close to 1.9, but we'll be a little bit off. The current likewise is close to 10 milliamps. This basically says my circuit design is good, ready to go to a breadboard. Another requirement for your PCB in 401 is that you need to add reverse polarity protection. What that means is if I take my battery and connect it backwards, I don't fry the circuit. I also need overcurrent protection. If I have too much current going in, a fuse blows. There's a couple ways of doing that. The first approach, this is what I recommend for 401, is stick a diode in series. What this does is if I put the battery in correctly, I try to push current this way. That's the correct direction on the diode. Diode turns on. Everything's fine. The diode does lose 0.7 volts, but that's not a big deal. I've got to dump 4 volts. I've got to break it down to 5 volts anyway. So if I don't have this in there, the 7805 dumps 4 volts. If I do have the diode in there, it dumps 3.3 volts. It's still dumping voltage to get down to 5 volts. What this does do is as the battery dies and the voltage drops, it's going to quit working 0.7 volts higher. So I need an extra 0.7 volts to overcome the diode. It's a little bit inefficient that way. I'm losing 0.7 volts just in my fuse. But what's nice about it is I've got to dump the voltage anyway. If I put the battery in backwards, the diode just turns off, no problem. Now, if I did something like take this point and tie it to ground, I'm going to have too much current. That's what the fuse does. The fuse blows if there's too much current. Fuses are expensive, so we don't actually use fuses in this class. We just use a 1 ohm resistor that kind of simulates a fuse. If you have too much current, the 1 ohm resistor is going to burn out. But what the 1 ohm resistor also does is if I want to measure the total current drop of your circuit, just measure this voltage. If I measure that voltage from V = IR, 1 volt is 1 amp. I'm also measuring current. So this is one way to design a circuit. To test it, I want to put the rest of the circuit over here. I don't really know what the rest of the circuit is yet, but what I can do is simulate it. Suppose I want to be able to drive a circuit at up to 100 milliamps. I could simulate that. 5 volts at 100 milliamps is 50 ohms. Just stick a 50 ohm resistor right here, and that'll draw 100 milliamps. Does the circuit work when my load is 100 milliamps? What I'll actually do when I build it is replace this with the actual circuit. But we don't know what that is for now. So this is kind of a model. As long as my total circuit draws less than 100 milliamps, 50 ohm is a pretty good model of it. A second option for reverse polarity protection is this circuit. What this does is if the battery is connected correctly, I've got 9 volts over here, 8.9 volts. You'll lose a little bit of voltage across the 1 ohm resistor. This is reverse biased. The diode turns off. So this has no effect on the circuit. The good thing about this design is I don't lose 0.7 volts in the circuit. If I were to connect the power supply backwards and make this minus 9 volts, what happens is now the diode turns on and I have 9 amps flowing through the diode. Keeps the voltage, instead of being minus 9 volts, this is now minus 0.7 volts. Keeps it small enough I don't fry the rest of the circuit. But what I do get, I get 9 amps. That'll tend to burn out the 1 ohm resistor, your fuse, or burn out the diode, or both. So this also works. My preference is this way, so if I connect it backwards, I don't burn anything up. I just have a diode turn it off. But either one will work. So that's diodes. Second thing to look at are transistors. Now, transistors can be used as electronic switches. For example, here, this is a circuit that we built a couple weeks ago. This is a PIC microcontroller trying to drive a speaker. Now, PICs are wimps. They can only do 10 milliamps. So here's a 2-key piano. You might be able to hear that. It's really quiet. Well, the problem is the microprocessor can only do 10 milliamps. If I add a transistor, that's this puppy right here, I crank up the power. So now instead of doing 10 milliamps, I can now do 1 amp. Maybe. A lot louder. So that's what transistors do. They basically act as switches or current amplifiers. They can take something wimpy, like a Raspberry Pi Pico, crank up the power, so instead of just doing 3.3 volts at 10 milliamps, I can do 9 volts or 5 volts at 600 milliamps in this case. So how does that work? Well, the first thing you need is a transistor. The ones we're using in Senior Design 1 are the 3904 and 3906 NPN and PNP transistors. Now these are current amplifiers. They have a current gain of 100. Actually, it's between 100 and 300. Worst case is 100. It can supply up to 200 milliamps. It's got a voltage drop, base to emitter of 0.7 volts, collector to emitter about 0.2 volts, and cost 11 cents each. So this is why we like them. They're cheap. And they also have quite a bit of gain. So I only need 2 milliamps in to produce 200 milliamps out. A Raspberry Pi Pico can do 2 milliamps. Now to use the transistor as a switch, there's kind of two different circuits. I can use an NPN or a PNP. So basically what you do is, if I just take the LED, connect it from power to ground through a resistor, ignore this right now, I have the LED turns on. Well, once that works, well, if that doesn't work, nothing's going to work. If that works, I can then break the circuit at two sides. I can break it on the low side or the high side and throw an electronic switch. If I break it on the low side, that's an NPN transistor. Break it on the high side, that's a PNP transistor. Now let's start with the NPN transistor. What happens is a transistor is a current amplifier. Kind of the way it works is an NPN transistor has got three regions, N, P, and N. This is your emitter, base, collector. Now normally there's no current flow, emitter to collector, no current through the LED, because this is a reverse bias diode in there. I can turn that on and off with the base. So if I apply a little bit of current at the base, these are going to be holes in the P region, flowing P to N. If holes are flowing P to N, I've got electrons flowing N to P. Now the base is really, really thin, so those electrons shoot right through. And what I wind up with is current flow. I've got current, since electrons are negative charge, flowing emitter to collector. So this current right here, IC, is related to IB and proportional. So if I, wind up with the equation IC is some constant times IB. If IB goes up and down, IC goes up and down. Beta is a function of the doping. If this says doping of 100 times the base, I have current gain of 100. So I'd have IC is 100 times IB. That's your amplification. So that's kind of how the switch works. The collector current is amplified base current. And base to emitter is a PN junction. That's a diode. That's what this symbol means. That's a reminder this is a diode, base to emitter. And that diode is all important. The current through the diode is what controls the current through the collector. Now to see how the transistor works, there's a thing called the load line. The IC, if I make that times beta times IB, as the base current goes up and down, the collector current goes up and down. The load line is, if I look at this circuit right here, if I take this point and ground it, I'm going to get some current, say 20 milliamps. If there is no current flow, I get some voltage, say 5 volts. Now, as the base current goes up, so I move up and down, more and more base current means I have a bigger voltage drop across RC. The voltage, collector to emitter, drops. So the base current kind of determines where you are on the load line. In the active region right here, IC is beta times IB. That's in the active region. I don't want to do that because, well, I don't want to operate over here because the transistor is going to get hot. The power is volts times amps. I've got a large voltage drop. This is going to get hot. What I really want to do is either operate here, this is the off point, current is 0, or here, that's the on point, or saturated. So to operate up there, I take the base current and push it up, push it up, push it up until I'm up here. If this is IB times beta, I'm trying to make IC bigger than 20 milliamps. I can't go bigger than 20. The voltage can't go negative because if it did, I'd be producing energy. I can't even quite get to 20 milliamps. I'm going to saturate at this point. That's where you saturate. That's the on point. So I really want to operate at 2 points, either on or off. Off, the current is 0. On, this is 0.2 volts. Not exactly 0.2, but normally what we do in electronics is assume number close to the 0, but not quite, 0.2 volts. So with that, I've got 3 states for a transistor: off, on, and active. Again, off is when the base current is 0. If the base current is 0, the collector current is 0. Saturated is when the base current is such that beta times IB is more than 20 milliamps. And active is in here, beta times IB equals IC, and the voltage is somewhere between 0.2 and 5. Now this is going to mean that this is actually how I test it in lab. If I have a transistor, I've got the emitter tied to ground. Here's the collector. I want to measure the voltage at the collector. If it's 0.2 volts, close to 0 but not quite, the transistor is on. If it's right around 5 volts, the transistor is off. If the LED is on and I'm somewhere over here, that's bad. That's in the active region. I need to adjust my design. And this is why the active region is bad. In the active region, you're dissipating heat. This transistor is not designed to dissipate heat. If you did that, it's going to get hot and you start melting your circuit board. So if you see these melt marks on the board, they're actually pretty common. That's somebody that tried to operate a transistor in the active region. So try not to do that. In terms of analysis, there's analysis and design. In analysis, I've got my transistor circuit designed. I want to find out what's the base current, what's the collector current for two states, when the input is 5 volts and 0 volts. Now 0 volts is easy. If this is 0 volts, I need 0.7 to turn on that diode. I don't have it, so the diode turns off. Current is 0, and that's your answer. IC is 0. That's the easy one. The one you got to work for is on. In the on state, when the input is 5 volts, this is a diode. Voltage drop across the silicon diode is about 0.7. So the current is 5 minus 0.7 over RB. Over here, assuming this is saturated, this is about 0.2 volts. If this is an ideal diode, this is VF. So the current IC is 5 minus VF minus 0.2 over RC. That's the collector current. And to check to see, am I saturated? I should have beta times IB more than IC. For example, suppose I had, this is 50 ohms, this is 1K, this is a red LED. Find the currents and check to see if you're saturated. Well, VB is 0.7. Assuming this is saturated, that's 0.2. IB then is 5 minus 0.7 over 1K, 4.3 milliamps. IC is 5 minus 1.9 minus 0.2. This is 58 milliamps. And to check if I'm saturated, beta times IB more than IC. 4.3 times 100 is 430. And 430 milliamps, that's your beta IB. Is greater than 58 milliamps. That checks. This is saturated. In Circuit Lab, I could check that. Design the circuit, plug it in, and what I'll see is that this should be 0.7 volts. It's actually 0.8118. Again, diodes are not ideal. It's 0.7-ish for silicon diode. It says 0.8118, close to 0.7. This should be 0.2 volts. In Circuit Lab, it says it's actually 0.09 volts. Again, that's good. You're close to 0, but not quite. The current flow, I calculated it, was 58 milliamps. When I simulated, I got 51.1 milliamps. Yeah, that's what you get. Again, this isn't exactly 1.9 volts. It's not exactly 0.2 volts. Put it all together, I'm not quite at 58 milliamps, more like 51 milliamps. If I made a mistake, let's make R1 too big. What that does, it makes our IB too small. In this case, IB is only 42 microamps. I'm trying to force 58 milliamps through it. What I have is 42 microamps times beta. That is 4.2 milliamps. That is not greater than 58 milliamps. So it is not saturated. It's actually active. In that case, IC is beta times IB. I can tell that I'm not saturated by measuring BC. If I measure BC right here, this is 2.8 volts. That tells me I'm not saturated. That should be close to 0, but not quite. That's not close to 0. I'm not saturated. To fix it, I need more base current. I need to take R1 and make it smaller. More current will give me, push you up the load line, push you closer to saturated. And again, the reason to do that, if I operate in the active region, it's going to get hot and melt. So don't do that. In terms of transistor design, what you do is you assume saturated, so this is 0.2 volts. Pick RC to set IC. Once I set IC, pick IB. Pick IB such that beta times IB is more than IC. Make IB such that I get more current than I need. I saturate the transistor. So for example, if I want IC to be 20 milliamps, I would say this is 5 volts. Here's a red LED. That's 1.9 volts. This is saturated, 0.2 volts. 5 minus 1.9 minus 0.2 over 20 milliamps is 145 ohms. RC should be 145 ohms. The base current, if this is 20 milliamps, IB has to be at least 20 milliamps over 100. This has to be at least 0.2 milliamps. So pick a number bigger than 0.2, less than 12, because that's all a Raspberry Pi Pico can do. I chose 1 milliamp. If this is 1 milliamp, here's that. Pick IB to be something that saturates it. I just chose 1 milliamp, nice number. Then RB is 5 minus 0.7 over 1 milliamp, 4.3K. Now when I build this, that 145 ohms is kind of important. That sets the current. The 4.3K isn't that important. The 1 milliamp, there's a lot of room for slop. Anything bigger than 0.2, less than 12 works. So if I don't have a 4.3K resistor, 4K works, 5K, 3.3K, anything in that ballpark is close enough. So this would be your NPN switch. I want 1 milliamp, 1K, 20 milliamps, 145 ohms. That's NPN. The NPN switch is what goes on the low side. If I want to put the switch on the high side up here, that's the PNP transistor. Now the analysis is almost identical. On the PNP, here's your diode. When the current flows this way, it turns on. To get this to turn on, Vn equals 0. 0 volts is on for PNP, and 5 volts is off. If this is 5 volts, there's no potential. No potential means no current. So rather than PNP, 0 volts is on, NPN, 5 volts is on. Otherwise, analysis is the same. RB, that's 4.3 kilo ohms. That's 4.3 kilo ohms. To get 1 milliamp, I have 5 minus 0.7 over 1 milliamp, 4.3 kilo ohms. To get RC, 5 minus 1.9 minus 0.2 over 20 milliamps, 145 ohms. Numbers wind up being the same. The one problem with that's with if you have 5 volts in. If I'm using a Pi Pico, then the NPN, PNP are similar. NPM is actually really similar. I'm going to have less voltage, only get 3.3 volts here at the NPN. Adjust RB to set the current. So if this is 3.3 volts minus 0.7 at 1 milliamp, this winds up being 2.6 kilo ohms. Everything else stays the same. The PNP is a little bit different, however. I can't take, let's go back over here. If this is a Pico over here, and apply 3.3 volts to turn off, that doesn't work. I want this to turn off when this is high. Well, 3.3 volts isn't enough voltage to turn off. If this is 3.3 volts, I still have 5 minus 3.3, 1.7 volts. This turns on. If that turns on, I have current flow, and the LED is turned on. So I can't turn this off with a Pi Pico. To turn off a PNP transistor, I need a level shifter. This is a circuit from last week. What the level circuit shifter does is 0 volts in gives you 0 volts out. 3.3 volts in gives me 5 volts out. Now that I have 5 volts out, it's the previous design. So this is just the one change with the pi pico. I need to bump up the voltage to from 3.3 volts to 5 volts. Then the PNP transistor works the switch. So that's kind of the idea of transistors and diodes. In summary, diodes can be used as valves. They allow current to flow one way, but not the other. We're using the diode for reversed polarity protection. Take your 9-volt battery, put it in backwards, and the diode blocks the current. A transistor, in contrast, acts as a switch. I can take something wimpy, like a pi pico, run it through a transistor, and I have a pi pico capable of 12 milliamps, now capable of driving an LED at 20 milliamps, or a speaker, in this case at 12 times 100, 1.2 amps. Allowing me to take a kind of wimpy processor and drive a speaker at some power, make enough noise to annoy your friends and neighbors. And that's week number 5 for ECE 401, Senior Design 1.